Okay, so now we are moving towards adaptive sinusoidal model. Now I will be much faster. I have 1 hour to teach you this, but now you know a lot. I have really paid attention. I think I went slowly. So for some people, very too slow, explaining the sinusoidal model. But I think you understand now more what is in the sinusoidal model, and that is the purpose of the school. Now we will talk about the adaptive then. Some aspects of adaptive. So you will see here a lot of names like QHM, adaptive QHM, extended adaptive QHM, and some applications. So the key, however, I'm telling you from the beginning, is this one. This is really the guy who makes the job. And then this one makes a very important job. And then this one also is important, but the key is here. If you understand this, then this is much easier to understand. And this is like logical step. But the key is this one. So I will spend time on this one. And then we will talk about applications, some key papers and references. Okay, sinusoidal model, you see, this I don't need to explain now. You know it, the general sinusoidal model, the harmonic model where we do constraint, we put a constraint on frequencies, k times now f0, how do we estimate the parameters? But there are some problems with these frequencies. If we know the frequencies, then this problem is linear, we can easily solve that. But if there are mistakes in our frequency estimation, then obviously we do not model very well the amplitudes and phases of the speech. Okay, so that is the motivation to go towards adaptive sinusoidal model. Okay, so this is the sinusoidal model that you know, complex amplitude, frequencies, and this is the window. Now, we can measure that in many ways. Subspace method or least squares method are different. This is based on the eigen singular value decomposition because it works on noisy speech. Least squares method, as we already mentioned them. There are also FFT-based methods like the picking, but also there is from Stanford University, the quadratic interpolated fast Fourier transform method. Again, the problem is that there is a mismatch. There is a mismatch between the real frequency that we assume here that we know and the real one. And there is a mistake. The mistake is this one, let's assume. If we know this eta will be important, and that is a function of k, that we make a mistake in all frequencies. Now, that was a frequency mismatch. There is now a frequency mismatch, so we don't have f, we have f hat. We introduce you now the quasi-harmonic model. The name we invented, but comes from a theory that de Prony in 1795 described. Laroche, working on audio signal processing in 1989, started using it. And then me worked with Laroche, and then I use it also for speech. And then my student, Pandasis, worked on that model. Not on this model, but on the model which is here. So what is the difference between this and this? Obviously, the only difference is here. Can you see that? Yes, you can see it. So this is H&M2. We have H&M1, H&M2, H&M3. This is really the H&M2, but we rename it to quasi-harmonic model, and now I will tell you why. First of all, I say, and actually one of the participants here, he used these models to separate speech, etc. And actually, this provides a very good model, so much good modeling. not however of speech, but of the time series. So that means even if the speech is noisy, you model also the noise. Why? What is the power of this to model this time series? It's not good, obviously, for separation, speech from noise. But a time series is very well modeled. What is the power? From where that comes from? Until the thesis of Pandas, we did not know. So we write for just one component, the kth component, the frequency version of it, and we have to take into account that this is a k, this is t times w. And if you have such a signal, then you are talking about the derivative of the window. So if you have a Fourier transform, x gives you, let's say w, lowercase give you w of f. That's a Fourier transform. But if you have t times w, then gives you the derivative of the Fourier transform. So these are the properties of the Fourier transform. So now we isolate just one component, the kth component, and we write it in the frequency domain this way. We do then this bk, it is decomposed into two components. One which is parallel to AK, that's rho 1, and another one which is perpendicular to AK, that is rho 2. Now, if I use this decomposition and write it back, then the above one becomes like this. And if I take into account this development, this is the Taylor series expansion of this one around this point. So then we can see the derivative here. That is why we use the Taylor series expansion. So here now there is the derivative plus some other terms which depend on the second derivative, and this is the rho 2. And this is rho 2, which is from the perpendicular projection of BK to AK. Okay, so now we recognize we have this term here. We have this. Now, if this is small, let's assume that if this term is small, then I can replace this part by this one, correct? So, if we do so if we say that this is so small, we can throw it away, then we can rewrite this approximated by this one. Just because we replace this one, this term, these two terms by this term. Now we are ready to go back to the time domain. So this is what we have found in the previous slide. We're going back to the time domain. Again, this derivative here means t times the w. We arrive to this equation. We continue to be, of course, approximation because we have rejected the terms of in the Taylor series expansion. And initially, we assume that xk, that means the kth component of the signal, has the estimation plus a mistake. So there is a mistake. So what we claim is that this rho 2 contains an information about eta, which is the displacement of the frequency. So our suggestion is that someone can estimate eta from rho 2. What is rho 2? Is the factor that we have when we project BK to AK, and this is the factor of the vertical, perpendicular projection to AK. So that is rho 2. So we will continue now playing with this rho 2. In short, we claim that this rho 2 is the key why you have such a very good modeling. However, that was what we had, and we dropped away the third term. And depends on the derivative of the window plus this ρ2, the magnitude of ρ2. That means if ρ2 is the mistake that you make, obviously if you do a lot of mistakes, like a huge mistake, this term will be high. So you cannot write this to keep only these two components. Or this is related to the bandwidth of the window. So what type of the type of the window or the analysis length that you have, these are also determine the value of the second derivative of the window at frequency fk. So what we would like a small value for that. Now we will talk only about the window, and that we know that depends on the length of the analysis window. For instance, for a rectangular window, this is analog to power 3 of the length. So what we want is a short analysis window, for this value to be small. On the other hand, we need samples, we need data in order to estimate in a robust way. What means robust? It is over-determined system, and when we move from time to time, if we have more samples in order to estimate these parameters, our estimation will be more robust. We will be focused more on the data and not on the noise. So that's why we need long windows. So length of the windows means an interaction between the bandwidth. So that bandwidth, we will use it later on. So we assume now that we have a simple model with just one component. Then the QHM of this is written this way. Analytically, we can estimate A and B, and this is the solution. And then eta, because it is ρ2 divided by 2 pi, is given by this one. Okay, so now we have an estimation of the mistake, and there is a mistake there. We have put a mistake, and this is the estimator of that mistake. Obviously, eta hat is not equal to eta, but it's equal to this one. So we might be wrong in our assumption. So let's plot this. We can plot that now. And then we can play with the t, etc. This is what we get. How to do zoom here now, if I do escape. Okay. So this is, let's say, what is the input mistake, and this is what is the error on our estimation. So if it is 0, that means we have estimated this eta1. Eta is the mistake that we make in the frequency, and here is in hertz. So you see that using a rectangular window, which is the continuous line, like this one, this cot, etc., gives that for around -10 or 20 to +20, we can recover because the error is 0, the error on estimating this mismatch. If I use now Hamming window, however, I can go from probably -100 to 200, that means 200 hertz bandwidth. I can still recover that. In short, if you have a component at 1000 hertz and you say, no, it's not 1000, probably it is 1000, and you say it is 1100, the system will find this 100 hertz as a mistake and move your estimation on the 1000 hertz. So that is what this means. Now, yes, please.
Are these graphs related to the sampling frequency in any way, or are
No, it is. No, it is not related. And again, this is. We can think about a bit of sampling frequency at some point, but it's not so much related now to the things that really can change this picture too much, okay? Okay, this is not anymore fundamental frequency and harmonics. We will come to that. It's just one component. Okay, we don't have harmonics. Just it is one frequency. And there is a mismatch on that frequency. Obviously, I say, for instance, that you have minus 100. Obviously, if you have like 50 hertz signal, you don't have this 100 to go to make a mistake. But if you, let's say you are in 2000 hertz, and you are 200 left and 200 right, you make a mistake, then this has a mechanism to correct, to find the real frequency. Okay? It's a spectral estimation method, parametric spectral estimation. Now, the good thing is that probably you can have a way like peak-peaking to try to find something better. And actually, indeed, if you don't have noise, a peak-peaking method can correct also. If I tell you it is 1,200 hertz, and then you do Fourier transform, you do peak-peaking, you say, no, it's around 1,000, just from peak-peaking. But that peak-peaking has not a mechanism. I mean, you have done that, it's over. This has a mechanism to repeat, to do iterations now. Because you had an initial estimation of frequency. Then you estimate A and B. You project B onto A. You get this ρ2 and you correct your frequency. Since now you have a new frequency, you can go back at the beginning and re-estimate and A and B. Reproject, get a new ρ2 and go again. So then you can see now, without iteration, and Hamming window is the dashed line that we had above. With two iterations, mainly we can also have good results in this area, like minus 150 hertz. In short, we can show that you can correct a mistake if it is within 1/3 of the bandwidth of your window. Now, what about robustness against additive noise? For instance, now we have 4 components, not 1, and we add noise. Then we measure the mean squared error in terms of frequencies and amplitudes in this way. And in order to do that, of course, now we don't have analytical solutions, but we can rely on Monte Carlo simulations to get estimations of frequency and amplitude. So now we compare the results to the best solution that you can have, which defines the bound, the Kramer-Rao bound. And we compare it with the quadratic interpolated fast Fourier transform, and obviously the quality of the quadratic interpolation fast Fourier transform, which is peak-picking method, is how close are these frequencies, these 4 frequencies that I mentioned here, how close they are, because then you have a resolution problem depending on how big is your analysis window, etc. So here we show the mean squared error for F1, F2, F3, and F4. You see, for instance, that the mistake for F1 and F2, it's not that big for the fast Fourier. No, this is actually error. So the error here is bigger for mean square, for Fourier transform, than compared to this one. So what does that mean? It means that F1 and F2, here you have bigger error. That means F1 and F2 are closer than what is F3 and F4. So the same analysis window, you have a better resolution to find F3 and F4. That's why you have lower error. But for F1 and F2, because they are closer, using the same analysis window, you don't have so well resolution, frequency resolution. So these stars show this method without iterations. So they perform better. And here, imagine, here you have peak picking. Here you put a mistake in the frequency. You put like 30% mistake, and you say the algorithm start with that, with 30% mistake. So you add an artificial kind of noise in the frequency, and you perform better than the peak picking already. But you don't perform better when the frequencies are apart, because the peak picking will find the frequency, while this of 30 hertz, I don't know, or 30% mistake, it is a big mistake. However, when you start now the iterations, this mistake reaches the Kramer-Rao bound for all the cases and outperforms peak picking methods. Once you do that, just with 3 iterations, you see a similar picture when you measure the mean-squared error of amplitudes. So same picture. Now, you see that as a function of SNR, how much noise you have added. So 0 dB means the same power of speech of these 4 components and the noise. Okay, more you increase the SNR, more clean are your data. Okay, so that is the main mechanism of the quasi-harmonic model. And why we call it quasi-harmonic model? Because you can start like as a harmonic assumption, but you know that as frequency increases, you make more and more mistakes in this harmonic assumption. Now you have a mechanism to change these harmonics with estimation of ρ2, which is the eta, differently in each frequency. So you move now your harmonics to next to the harmonics, so like quasi-harmonics, near the harmonics, but quasi-harmonics. And it is robust against noise, and there is a nice communication which has been published with other researchers that we show that indeed this iterative quasi-harmonic model is equivalent to the Gauss-Newton method, or approximate Gauss-Newton method. And we can show that this quasi-harmonic model, if you take into account also ρ1, not only ρ2, it can be shown that it is, it can lead you to a reassigned spectrum, which is the better spectrogram that you can have. Now, I will not go to these details. There are some papers that show that. But nevertheless, it shows that Gauss-Newton method works similar, like the quasi-harmonic model. This is a reassigned spectrogram. Again, it relates to ρ1 and ρ2. What is the reassigned spectrogram? You start with a spectrogram, and then you take, you move a bit your estimation over frequency, over time, and you group things together, so you have then an enhanced spectrogram. This is the reassigned spectrum, because you reassign in the time frequency bins new values. This is reassigned spectrogram. And we can show that quasi-harmonic model provides a mechanism to estimate this reassignment, that means to displacement, to estimate displacement over time and over frequency. And these are the displacement that you do over frequency and over time. But again, this is and mainly this shows the the equivalent of reassigned spectrogram and quasi-harmonic model. It's okay. Now, we move now from the quasi-harmonic model to adaptive quasi-harmonic model. Look at this. This is now the quasi-harmonic model. You can see that this function here, exponential, defines the space of these exponential functions as a function of fk. And this is constant. This fk is constant during the analysis window. So we can think to make this variable. And this variable, then phase, it depends on the frequencies. Obviously, it is the integral of the frequencies. So if now these frequencies come from a time-varying information of the signal that you want to model, then these functions are actually adaptive to the signal that you analyze. That is from where we go from the general quasi-harmonic model to adaptive one. And graphically, this is what is quasi-harmonic model. Probably this is what they told you, that it's the frequency, and then you make this correction and you find this bold line, and then you are happy. But this is constant over time while the frequency of the signal moves. It's not really constant during this analysis of 2T analysis window. Okay? So the question is now how to go from this bold line here to another bold line that changes over time. And this is the adaptive. So we can, for instance, do do sample by sample estimations, or we can do a sampling every 5 or 10 milliseconds, depending on how many features we want to extract, and depends on the application that we want to apply it. Like, for instance, for quality estimation of voice, for voice quality assessment, we can do every sample, or we can do every 5 or 10 milliseconds if we work on coding or speech synthesis. And then we have the estimations, when, for instance, we have these higher rates of, and then we do linear interpolation of amplitudes. Frequencies are interpolated with splines, and then we apply this integral, and we get the instantaneous phases. And here is graphically again an example. Imagine that this line here, if you can track it, like here, goes down, then goes up, is the instantaneous frequency of the signal that we analyze. And we have done some estimations which are not so well in some points, but in some points they are good, and this is the other line, this one which contains these crosses. Now, by doing this spline interpolation and estimation of the instantaneous frequency, we can re-estimate AK and BK, and then go to the next iteration. So we are very closer now to what was the input, and now even much closer with just 2 iterations. And we made a test on an AM-FM parametric model, as it is shown here and here. This is the AM, this is the FM part. And we introduced to the model already a mistake of 30 Hertz, 35 Hertz. And we use Hamming window. And we analyze with sinusoidal model. And we have here, this is 10 milliseconds, and frame rate is just one sample. And we measure the mistake, the mean absolute error, on amplitudes and frequencies in hertz. So you can see that the quasi-harmonic model, if we model it every 10 milliseconds, we have slightly better than the standard sinusoidal model. If we go, of course, every sample, then we have practically no mistake.
Just
yes, please.
Perceptually, can you, if you listen to these the samples modeled this way, do you really hear?
Yeah. Okay. For the sinusoidal model, the average signal to reconstruction error ratio is around 17 dB. With the adaptive quasi-harmonic model, even if you go to 5 or 10 milliseconds window, it is around 31 dB. Above 25 dB, you cannot feel any difference. So that means in sinusoidal model, there will be moments where we can feel a difference. But for the quasi-harmonic model, no. Now, of course, someone can say that you use, however, more parameters, while the sinusoidal model does not use so many. But this is not true. Actually, we use more parameters during the analysis stage. So we do all of these estimation of A and B's, etc., and we correct. Okay, once we do that, then we can construct the AM and the FM part. When we have the AM and the FM part, we can sample it at the frequencies that are used, let's say, or other frequencies, use the number of frequencies that are used in the sinusoidal model. So at the end, when you do the synthesis part, you will use as many parameters as the standard sinusoidal model. But these parameters are enhanced, are estimated through this procedure. So then, as I said, we go to instantaneous parameters, AM, FM components, and this here it shows analytically how we estimate the instantaneous amplitude, the instantaneous phase, which obviously it is a function of this instantaneous frequency. So, in short, we say that probably we can do an AM-FM model. And then we show also that by saying, okay, this is a standard AM-FM model. We make another Taylor series expansion of this phase, assumed phase. And this is what we get from the Taylor series expansion of this function. So if we consider the instantaneous frequency of the kth component, but at the center of our analysis window, where t equals to 0, then we get this one. And previously, if we see the equations from the instantaneous frequency, what we estimate, we know that it is the frequency that we assumed plus this ρ2, which is the parameter that we extract from B. In short, if I have A and B, then I can correct my frequency, then put this back into, since I have that, I can construct this, and then I can have a better estimation of my FM part. So let's see plot now the original signal and the reconstruction error as a function of time from the original and the sinusoidal model. So now you can see from where the 17 dB signal to reconstruction error ratio come from. You have a lot of mistakes in some areas. Now if you go to the quasi-harmonic model, you do better. But when you go to adaptive quasi-harmonic model, then really the error is very, very small. That's from where the 31 dB signal to reconstruction error ratio comes from. Now, we have done also tests on signal to reconstruction using AM/FM, so that means we estimate now the instantaneous amplitudes, we estimate the instantaneous phases, and we test it on real speech now, on 5 minutes of 20 female and male voice speech from timid database. And here is the average signal to reconstruction error ratio that I mentioned before. The sinusoidal model has for male voice 17, for female 21. Why there is such a difference? Why for female it works better, you think? Yes.
Harmonics are more sparse.
Yes. The harmonics for female voice is sparse. So it's for the same analysis window, let's say, then you have better frequency estimation. So frequency estimation means better reconstruction. When you use quasi-harmonic model, I mean, the result is much, much better for the same number of K for both systems. Now, if you use adaptive quasi-harmonic model with 3 iterations, then this is the signal to reconstruction error ratio. Again, above 25 dB, I don't think there is human ear that can detect the differences between the original and the reconstructed. So, what we have so far, we have an AM/FM representation of speech, but also can be applied to other sounds, and we have published results on audio. But it is high resolution, has K components there, where K can be like 80. So it is a high resolution AM/FM decomposition of speech or audio with a parameterization of the AM and FM, which is under control. I can control it now. It's not like from Hilbert, that, okay, I've got another signal, what I'm going to do with that. Here I have a full control of my AK of t and phi k of t. In short, we improve the analysis and we do AM/FM synthesis as we do it with the sinusoidal model, but we have a better analysis. So now we go to the extended adaptive quasi-harmonic model. You probably now recall that the adaptive quasi-harmonic model is this one. But this, if I isolate it from the first part, which is inside the parenthesis, this part is a phasor which has amplitude 1. I can replace that with another phasor which uses another amplitude information. So now this is a phasor that I will adapt not only its phase component, but also its amplitude component. And this is a function of t. So this is like a weight which is also here shown, another weight. This is also another function of t. So then you have two functions, like you have now a factorized model of speech. First factor, second factor, and then this term. Of course, some people can say, why you don't multiply this? And this is, last year, for instance, people say, why you don't multiply this? So, oh, of course you can multiply. Then you don't have any more factorized representation. You have just one factor. And then if you put them all this together again, you don't have any factorization. You just have samples. The question is how you can model all these samples in a factorized way that can provide you a mechanism to control speech or detect things on speech. And that is the motivation. So here is now AM/FM with two components. You see here the amplitude modulation and the frequency modulation. Imagine now the adaptive quasi-harmonic model adapts to the frequency content of the input speech. So the FM part is very good. The dashed line is the estimation. The true is the solid line. So we are on top of each other. So it's a good frequency estimation. So the FM part is good, but the amplitude changes very fast, and we do not have a very good estimation. Now, if we add that alpha of t, we get this one. So we kept the FM part is good, and the AM part has been improved by far. Now, this is again original speech. This is reconstructed using the adaptive quasi-harmonic model, and this is the extended adaptive quasi-harmonic model. Now, if you look this, and this, they look the same. But now, if we compute the mistake, the error, then you see this is the error that we had from the adaptive quasi-harmonic model, which is much better than the sinusoidal model. We have already shown that. With the extended one, we have much less error. Again, here you have AM components FM. You can sample them, and then you can reconstruct as simple as an AM FM model like the sinusoidal model. Now, we use that for a specific application, which is very important for the quality of the reconstructed speech and speech synthesis. For instance, imagine that we have this release of T sound. Nothing, because I keep my lips closed, and then I release time. When I will do sinusoidal model, then I have this pre-echo, which is mentioned here with the red one. The pre-echo is not really a problem of these samples. It is that this release is not anymore so strong. And probably you are masking this. If this goes like here, outside of the red circle, then you start perceiving that because it is beyond the masking threshold of backward, masking threshold of this click. But if it is small, like inside the circle, you don't perceive this pre-echo. So where is the problem? The problem is that you don't have a big burst here, a big change in the frequency. So you don't have a clean t, k, p sounds. And these are very important for the intelligibility and the quality of the synthetic speech. So when we do adaptive quasi-harmonic model, we improve by far this. That means we remove energy from here to here, so that now we have a very good click, release of T. And if we do the extended one, mainly there is nothing here. Every energy is here now. So that's good. Clean, intelligible sound. Why it is like that? Because if we now plot each individual trajectories of frequency components, for the sinusoidal model, we see that this is the release time. This is the dashed line. It is labels the release time of T. So you have many components before. That's why it makes this, how I call it?
Pre-echo.
Pre-echo. Yes, pre-echo. Thank you very much. If I do the adaptive quasi-harmonic model, I also have components there. But if I do the extended adaptive quasi-harmonic models, then mainly there is nothing before the release, and everything is after. And we did some tests on Putu, Ku, Budu, Ju, Gu, with sinusoidal model, adaptive quasi-harmonic model, and extended quasi-harmonic model as a terms of signal to reconstruction error ratio, and this is in dB. And you see that indeed, in these areas, the sinusoidal model cannot handle that because it just has some of sinusoidal. It has no any power to make something discontinuous. Everything is continuous. Adaptive quasi-harmonic model does better, but very good is the extended model. And obviously, this is very important model when you have percussive sounds, like model audio. This is very important. But also for speech, we have all these sounds. So now we can do we have now a fully parametric model, AMFM, that we can synthesize similar to the Sinusoidal model, but we have a very good analysis, very powerful analysis. So we can do a lot of things, like high quality time scale, pitch scale modifications, even modify inside the glottal cycle things, like opening, closing, etc. Remove pre-echo, and that is important in terms of, especially in time scaling and intelligibility. And we have published work on quasi-harmonic models on emotion detection. That is also provides very good results. Obviously, you can then control the emotion because now you have a full control of these parameters. In speech synthesis, it can be used for unit selection, for fast synthesis, smooth trajectories, high-quality prosodic modifications whenever it is necessary, and voice conversion. Statistical modeling, yeah, obviously you can do that. The point is how to model the acoustics that come from the AM and the FM. If you solve this problem, then you can use this for speech synthesis. And anyway, Sinusoidal models, and we will see later on, work nicely with DNNs for speech synthesis and other models. Speech recognition, this system has not been used for speech recognition yet, but it is robust against noise. So that might be a very good application going towards noisy-free filter bank estimations. Such a powerful model, you can use it in many ways, and a very important application is that of speech pathology. That means from the speech sounds to detect what are the problems of people. And we found very good estimators for jitter and shimmer. Jitter are variations, abnormal variations on the pitch, while shimmer are abnormal variations on the amplitude. And vocal fatigue, we were to some extent successful here, but we are not that happy. We had, however, a robust estimation of spasmodic dysphonia. This is a very important pathology. And we developed a time-varying model for the estimation of the vocal tremor. That is, I have not seen any other model that makes this possible, the time-varying estimation of the vocal tremor. Now, there are some key papers to read if you want to... oh, that's already zoom in. So, the first one is the Sinusoidal model. This one describes the quasi-harmonic model as AMFM, adaptive AMFM, signal decomposition. Then we wrote a signal processing letter where we described the estimation of this, the power of B, projecting B into A, etc. And Stoika was one of the reviewers of this letter, so he wrote some comments. And the editor said, these are good comments, can you reply to the comments? Then we replied to the comments, and he said, why not to make this conversation between you to more letters, so that people follow the communication between you. And that is very, very nice. It sounds like 18th century communication between researchers. But I think that's beautiful. This is beautiful communication with Stoika. And then recently, in 2013, with Gilles Decotext, we went one step further and we made possible to remove quasi-harmonic parts and go back to the harmonics, but using an adaptive now model. And this is a very powerful model for speech. So mainly that's it. So these are the key papers to read. These are some references that I have in the slides. Again, I want to say big thank to Thomas Quattieri, first because he wrote a very nice book. Second, because he gave me the, authorized me to use some of the pictures from his book. This work really has been done, and I say here for Tom, okay? And my ex-PhD student, George, that has interactions with you, he developed the extended adaptive quasi-harmonic model, while with Yannis Pandazis and Olivier Rozek, was before France Telecom, now Voxygen, a startup on speech synthesis. We worked on the quasi-harmonic model. With Vasilis Tsiaras and Yannis Pandazis, we showed the connections between the Gauss-Newton method and the reassigned spectrogram. And with Gilles Decotex, as I mentioned, we went to adaptive harmonic model. So these are the acknowledgments that I have to say to these people. And thank you very much also for your attention to this part. It was a bit probably difficult to follow, but I hope I gave you a good idea of what is the adaptive quasi-harmonic model. So thank you very much. Are there any questions?
Quasi-harmonic model, once you get the estimation of the frequency correction term, are you like dropping the BK?
Yes, I can drop the BK. I can use just now, yeah, because at the end, when I do the synthesis, I do with the AM, FM part, so I don't use anymore.
So it means after dropping a number of parameters, it's still the same as the sinusoidal model.
I arrived to a better AM, I have an estimation of the AM, FM part, and then if I have AM and FM, I can simply use the sinusoidal model.
And the difference between the adaptive quasi-harmonic model and the quasi-harmonic model is that
it is that the quasi-harmonic model makes the assumption that the frequency is constant. And you can make corrections, okay?
Does it mean that you're like interpolating the frequency from each frame?
Yeah, I mean, but from here to here, yeah, I interpolate, but in this development, as I mentioned, graphically, in theory, I have just constant. In practice, if I want, then I have to interpolate. But this is not adaptive to the signal. It is adaptive. It is a solution once you have this sample and this sample. You have somehow to make a line. Now, even if I don't do simple linear interpolation, but I do a spline, etc., even that is not adaptive to the signal. It is correct here and here, but all the other samples are not correct. Of course, I can make assumptions. Like, for instance, Quattieri makes assumptions. And we will see also Yannis with Vokine makes also some assumptions of F0. And it works. Just we wanted here to have a full control of the signal. That's why now we'll learn the frequencies. We do a first interpolation, then we re-estimate the points. And then we have a better estimation of how the frequency changes over time, not with a specific mathematical model, but based on the samples, and of course some assumptions of splines, but much better, because we can have also longer window there, to estimate the time-varying frequency information of the signal that we analyze. In that way, it is adaptive. Yeah.
So I'm not sure if you understand why it's so robust to noise, given that we are characterizing all of the noise, which is the non-harmonic part of the speech, as well as if there is noise in the signal, as one thing. So why is it so robust to noise? Because you're not differentiating between the channel noise and the actual.
You know, when you have noise, for instance, you have some components which are above the noise level or below the noise level. And the system, as it was shown, can overcome the problem of additive noise to some extent, which means that has a mechanism to estimate the frequencies. So that means in these frequencies that are, you estimate where are your components. This is the first step in order to be robust against noise. So you have a mechanism to correct that. So you know now that your components are in this, and this frequency, let's say 4 components, okay? So this is the first step to be robust. The next step is to estimate the amplitude. So I'm not very happy estimating this amplitude in this way, but this iterative approach, once you estimated the frequencies and you are 0 dB SNR, so that means you are mostly, in some components you are higher, below, or some components you are above the noise level, you will have a good estimation of amplitudes, and here not such a good estimation. This is, let's say, below the noise level. In this way, the amplitude is not going to be as good as for this one. But nevertheless, the component, the frequency of the component will be good. In that sense, it is robust. If you want to increase more the robustness to go to ASR, you have to correct also that amplitude here in probably iterative approaches. Like there are expectation maximization methods to try to optimize this. We have not done it, however. But the first step, and it is because of the frequency estimation. And I have not material here on HM3, but we can talk, okay, after. I will be happy to. Yeah, indeed, actually, H&M has been used for at AT&T to do speech synthesis and even unit selection we try there. Okay, and H&M2, some people are trying now to put it in speech synthesis, but no one has touched the H&M3 yet. And we were discussing about previously during the break what are the benefits of H&M3, and since you asked just headlines, is that if I take a signal and I add noise, then the H&M2, which is the adaptive quasi-harmonic model, but not exactly because we were not doing iteration at that time, just simple AEK, BK, the simple quasi-harmonic model, it models also the noise that you put on the signal, the additive noise. The interesting thing is that the H&M3, you put the noise and the signal, and then you estimate. The estimation is really, we are talking about not noise uncorrelated with speech. And then H&M3 gets an estimation, a good estimation of the signal and estimation of the noise. So it separates the two components.
So basically the extra polynomial coefficients which are actually characterizing some.
Yes, but there is a very important information here that these extra are real numbers, not so the system continues to be linear, while the H&M2 is non-linear because the AEK and BK are complex. That's the difference. Okay. So I think H&M3 has nice potential for even more robust, and if you combine that with kind of expectation maximization algorithms for the estimation of the amplitude as well, then I think you will have a good one. That I'm thinking about additive noise. How to do it on channel noise, that convolution, that requires a bit more discussion. Okay, so thank you very much for the comments.